time to start. How are you today? Fine, good. So today's lecture is devoted to the difficulties of training deep models. So you want extract deep features, train ever deeper models, and yeah, different difficulties arise, and then there are several ways how we could tackle that. So the maybe most known difficulty is the problem of vanishing or exploding gradients. So let's see what it is. Suppose you have many layers, so a network is consisting of many consecutive layers. So it is kind of composition of linear and nonlinear transforms. And then we know its gradient is the product of Jacobians of all the layers. And now what can happen? So if these Jacobians, if all of them are contractive, that means that sort of the shrinking the space of the inputs all the time, maybe along some dimension or along all of the dimensions. Then if you stack more of such layers, then this shrinkage effect will accumulate. And for example, if in each layer, so this is like a canonical example, I would say, because people were initially, they were trying to learn neural networks with the sigmoid activations, right? So if you have this sigmoid activation, then actually we notice that its derivative is at most 1/2 at this point, but at other points it is smaller than that. And if you stack many of such layers, then in this backpropagation you accumulate the product of all these small things, and the gradient is said to vanish with when you increase the number of layers. So basically the gradient which goes into this layer, if you want to train these parameters, will be much more smaller than the gradient that goes to the layer which is closer to the loss. So, and these kind of the shallow layers will not train or will train too slowly. So in practice that's not training well. And a contrary example, when the gradients, this exploding gradients phenomena, that's not occurring so often with, I mean, it's not an issue with nonlinear transforms, because typically we use some linear transforms which have bounded derivatives. We rarely have maybe exponentially growing functions, right, that have an unbounded derivatives. That would be bad, maybe. But what we have is maybe linear layers, and a linear layer may also be like a contractive or expanding, depending on what's its singular value. So if the singular value there is a singular value larger than 1, then at least in one dimension it will be expanding the space of the inputs. And if you stack many of these linear layers, again we can have this imbalanced gradients, so that maybe the gradient, if all of them are expansive, then the gradient in the shallow layer will be much more bigger than the gradient in this last layer. So it is first it is imbalanced, and the second it can even like numerically overflow or something like that, if this accumulated effect of these scales is too big. All right, so that's one problem, one side of the problem. Maybe the other very related problem is some degeneracy in statistics of inside of the neural network. So in the previous slide we discussed about the scales, and we discussed about vanishing or exploding gradients, but these gradients depend on the operation point in which the gradient is computed. And of course, in the neural network, there might be some operation points in which the gradients are actually vanishing, and we cannot avoid that. then what we want actually from our models is that this doesn't happen for all of the data, right? So we want that if we consider on average over the training data, that we want that the gradient would not vanish on average over the training data. And for that reason, we care about, like, okay, statistics of the gradients over the training data and statistics of activations over the training data. So maybe this example illustrates the point with the sigmoid activation. So if for all our input data in some layer, the pre-activation, the input to this activation is distributed like this red distribution. So it means, so this is the, so imagine this is like empirical statistics. We take many images, propagate through the network, and build a histogram of where the pre-activation lands. And if almost all of them are concentrated like far away from zero, then of course the gradient will be vanishing, right? And then we have a problem. And similarly, if you use ReLU activation, if these statistics of before the activation, if they are too much shifted to the left, we also have a problem. Then the gradient vanishes, but also the output of this neuron will be always zero, so it's kind of degenerate case. So we can call it a dead neuron that always outputs zero, so it has no useful function. For it to have a useful function, for some part of the inputs, it should produce a different output, right? So we don't want neurons that always stall at the same output, because we can replace them by a constant, right? And now, if you take a ReLU network, so if you take a ReLU network with this activation, maybe it would seem that the scale doesn't matter much for it, because, okay, if it's sort of a little bit, it's homogeneous with respect to the scale. So if you scale the input, the output scales. And yet, if we like initialize all the weights in this neural network with some constant scale, then we can observe that if we propagate through consecutive layers of the linear layers and then this ReLU layers, and we look at the statistics of the, okay, what is the average pre-activation and what is the standard deviation. So, okay, so this distribution we can capture by these two statistics. So if you look at the statistics, we can observe the following. So that the actually mean will go to zero. That means that, okay, somewhere we hit these cases where all our distribution in some layer was mostly on the left of the ReLU, and then in the next layer the output will be almost zero, and the variance goes to zero as well. So this is, yeah, so this maybe corresponds to the statistics after applying ReLU to such the input, right? So then the result to the statistics will be zero and highly concentrated, right? And okay, so this happens, and now it's an issue, right? Now, what do you think we can do to improve the training of neural networks? Maybe think more generally if you have a deep model, and I've pointed you to maybe two issues, but maybe this is not all of the issues, and maybe let's try to think what we can do to improve the trainability of deep models. And I've brought up one point. Okay, let's use ReLU function instead of sigmoid. This people have noticed somewhere it was an important step in deep learning. At some point they started to use this function, which was not biologically motivated, or maybe it has been motivated later on, but initially they were using a lot of this, but then they noticed, okay, with this one we actually have much less of this vanishing gradient issues, and then things started to work. Yeah, fine, we can do that. What else can we do? Sure, yeah, if you know something, just tell it.
Sort of normalization, so we shift those values like into the area of the function where we don't have these problems.
Yes, yes, we will talk about that, yes.
We can use some different architecture, like residual, I think it's called.
Okay. Yes, it will help as well, yes, and we will talk about that as well. All right, okay, so maybe mainly that. Yeah, I made the list, so we can talk about how we initialize the scales such that we don't have these expansions or contractions. We talk about normalization that can do this in the data-driven way. And like we're gonna relate this to also sort of what you can do with if the training is slow and inefficient, you can say that is a problem of optimization, and then you kind of want to think about adaptive optimization or preconditioning the gradient descent, but it's actually we will see that it's very related to this initialization and normalization question. So actually by doing the proper initialization or the normalization, you addressing already in a way the question of good preconditioning for the gradient descent. So we're gonna couple this to that a little bit. And then, okay, this is funny, but it's true. Like you can just simply increase the width of the network, and then it will train faster. You can discuss that. And then, yeah, you can do residual connections, and maybe if taken in generally, you kind of need good architectures that fit well to the task, and then they are learning faster, and then they are generalize better. But these ideas about residual connections, they are more or less universal, so this you could apply to nearly to any architecture, and so it's can be considered as a sort of a general technique. It's applied in transformers, in other models, right? Okay, so we'll go through the weight initialization techniques and the sort of approach. How do we do it? And we're gonna tackle. So the approach is that we're gonna tackle this problem of the activation statistics, and then hope that if you do that well, then also the vanishing gradient problem will be addressed well as kind of automatically. So if I have some images on the input, we often kind of standardize this data to have in, I don't know, in each pixel or in each coordinate of the input, on average our data zero mean and unit variance. And this is a good preconditioning for also for many classical algorithms like PCA or linear regression. It's also often done for neural networks, also maybe with some normalization techniques that's becoming could become unnecessary. But to start with, the input data is often standardized to have to have something like normal distribution. for each of the coordinate independently. But then also what happens if you take some data vector and then the weights we're going to initialize randomly, right? So this is for multiple reasons. We cannot initialize them as constant because they will be just lots of symmetries. It will not train well, so we gotta initialize them somehow randomly. It does not matter much from which distribution we initialize them randomly. What is going to happen if we add many random weights multiplied with these inputs? So if you compose this scalar product with random weights, then due to the this central limit tendency, the sum of these many random variables will tend to Gaussian as well. So this is kind of works already. So you just need to initialize weights randomly, and like also the easy thing here. So if you initialize the weights such that expectation of the weight vector is 0, right? So we just take like 0 mean normally distributed weights or 0 mean uniform weights. Then also pretty much automatically, like get a better chalk. Pretty much automatically also the expectation of this scalar product will be 0, and that's regardless of what was the distribution of x. So as long as these weights are drawn randomly and independently from the data, and they are, then this will be product of the two expectations, and then it will be 0, right? So here we are considering one neuron. In the next layer we have many of them, and that means that, okay, for each of them we will have kind of normal distribution with 0 mean, but the scale might be different, right? And what's the scale will be? The scale will depend on the number of the inputs, right? And then on this kind of variance of the weights that we are using. And okay, so this is what we have here in the slide. So suppose that weights are independent, identically drawn with 0 mean and some variance, denoted as omega. And then we want to write, so what is variance of this linear transform? So this is like variance sum over I, wi, xi. Maybe, can you help me? Do you know how do I deal with this if it is a sum of independent variables? It's like basics of statistics. Yeah. So it will be sum over I, and then the variance of you get variance of wi, xi. So variance of product is a little bit more tricky. But in this case, because both weight and the inputs have 0 mean, then this is going to be expanded as just product of variance of w and x. And x we assumed, so x we assumed was standardly distributed. So in this case, we obtain that it will be sum over of the variance of wi alone. So this is going to be like n omega, right? So that's n input units and the variance of this one weight here. And then what these guys did, the Gloro and Benjo, they said, oh, okay, let's assume that they were considering network with this hyperbolic tangent nonlinearity. It has derivative of 1 at 0. And I say, okay, let's assume it's just identity. And then this is going to be our, so then this nonlinearity kind of is preserving the scale, and then we only care about the linear transforms. And then our rule is going to be, okay, so we want the variance of the output to be also 1. So you want this to be 1, right? And then our initialization is going to be like, okay, let's say this omega is 1 over n, just like inversely proportionally to the number of inputs. And then that's already good to start with. And it was helping, and it was training. Furthermore, the same sort of reasoning could be applied for the forward propagation and for the backward propagation. So in the forward propagation, we have here like the result of this linear transform is this x multiplied with the weight vector, scalar product. So this is our forward propagation, and we've derived. Okay, yeah, I was assuming that the variance of the input is 1 already. And we say that, okay, we want the variance of the input to be preserved like this, and so there is this relation between the variance of weights and the number of inputs units. But also what happens on the backward pass, the gradient here gets multiplied with the transposed weight matrix, if you like, here in this for this layer. And then it has to be multiplied by the gradient of the nonlinearity function in the chain rule. But that is assumed to be 1 at the moment, right? So it kind of doesn't matter. And we are getting like pretty much the similar relation for the backward pass. So we could reason that if the gradients from the loss function, even if they were not normally distributed initially, after the first linear transform, it gets accumulated here, it's kind of normally distributed. And then we could talk about like preservation of the statistics through the layers backwards. And then the equations for the backward will be similar. Only like here, the number of things which are combined together with the weights is the number of units in the next layer. So here for the forward propagation, it was the number of the inputs, right? So this is the number of units in this layer. But for the backward propagation is the number of sort of outputs because we are going backwards. And so to have this stability for the forward propagation, we kind of need the variance inversely proportional to the number of input units. But at the same time, for the backward stability, we kind of need the variance to be inversely proportional to the number of output units. So it's not clear which one to choose and which one to prefer. And okay, so the empirical rule was this. Okay, let's take sort of 1/2 of the, or the inverse of the 1/2 of these two numbers. K and K. Okay. Yeah, indeed. Yes, yes, I agree. From the picture, it looks like k minus 1 and k plus 1. Let me take it offline.
Maybe just vary the mouse. Maybe there should be, like from the line before, it would be this k plus 1, omega k plus 1. Maybe. Because it's just like taking the line from above.
I think the picture is wrong because the green scene is the like we are talking about initialization of the weights in one layer, right? Whereas the green and blue are in the two different layers. So maybe the picture is the right picture. What we need is I got a green and blue. Huh? 1, 2, 3. 1, 2, 3. So the right picture that we need is this. Okay, let me make a different number of these things. And this, right? Because we are talking about the weights in this particular layer. And anyway, in these models, so we discussed in the vision models, you would expect maybe like 5 stages of this resolution reduction. So there would be not so much differences between of the number of the yeah.
What you the new picture that you create is essentially the same. It just moves the index a little bit. I think.
Yeah, we are discussing why in this formula there is these two consecutive indexes k and k minus 1. You see, so this is would be in the picture. This would be k minus 1, and this is k, right? And this corresponds to this formula.
Yeah, I agree with that. I just thought, well, the line that's above, that there should be the nk minus nk plus 1 omega k.
Just take this line, assume that they are the same, these variances, then you get the line below, but with the different indexes nk plus 1 and omega k plus 1, which is like what you would need, and then you combine these two. Okay, maybe.
Yeah, you're right. So it's partially it corresponds to that figure in the slide, and partially it is. It was from Boris Flachfrom actually the last year. This piece I should have not copied everything. All right, but yeah, what I wanted to say is that typically we have maybe these 5 stages of doubling the number of channels. So there would be like a limited factor that comes in the amplification of these statistics due to preferring these inputs or the outputs. And that would be okay still for the training. You could like still between these stages of the increase of the channels, we could pack lots of layers that have the same input and output, and for that we have either the rules would be correct. Yeah, so we could do that. So we have this rule for the variance of the weights. We could do the normal distribution with that variance, or we could use a uniform distribution. But the uniform distribution, so the variance of the uniform distribution with the interval from minus d to d, the variance of that distribution will be like what's that, like 1/6 of d squared, something like that. And so it implies, okay, so you gotta use this setting for d such that the variance of this uniform distribution is matching to what we want. Then these are the equations then for initialization of the scales. Let's go on. Now, yeah. Yeah, there is some mistake, yes. Yeah. Right, so now this we did like following the Gloro and Benjo, and now how do we deal with nonlinear activation functions in the network? Then because they can kind of spoil this all propagation estimates for us if you have different nonlinearity functions. The general recipe is as follows. So we make similar assumptions. So we assume that the input to a layer is specifically the result of this vector, result of the multiplying by the random weight matrix of some inputs is normally distributed. So this we call pre-activations, and so we expect this to be normally distributed. So it makes sense kind of to talk about pre-activations, then activation function, and then pre-activations in the next layer. And so I assume the network is composed of many layers like this, and let's look at the pre-activations before the non-linearity and then in the next layer after a linear transform. And let's assume these are normally distributed, and assume the weights are also normally distributed with some variance. Now, we already talked about this, so this is going to hold, right? For yeah, what is going on? So this was one layer. Yeah, maybe I need a new figure. Let's say we had like AK, and this we assume that these are centered, like normal distribution 0, 0, 1. Then we have the nonlinearity function. And the nonlinearity function can transform this distribution, like squash it and or reshape it, and it will not be. It may not be zero mean. It could be something, right? Yes. Yeah, but then we have like the linear sin WTXK, and we take this distribution and multiply it with multiple random weights and some from the many inputs. And this is going to be again normal, but or tending to be normal, but may have a non-zero mean, right? So in general, so could look like this. But this identity still holds, which was on the board, but we also have this on the slide, that if the weights are zero mean, then this factor out, and it doesn't matter what was the distribution here, then the result will be zero mean. Only the scale could be then somehow inappropriate for us. And now to compute the scale, so what we need, so we are breaking this variance. So this time there is no, so this input is not zero mean, so there is like a little bit more complex formula for the variance of the product. And the formula is that it's the variance of the first variable times the second moment of the second variable. Because the weights have zero mean, then at least it is still like a simplified formula. So this is what we would need to know. What we need to know about the activation function is that like the second moment of the activation of, like expected value of the squared activation function if the input is standardly distributed. So we need to compute this value, and this can be computed for ReLU analytically. Maybe you can have an exercise in the seminar, so to compute the sort of squared activation function is this, and then we are gonna compute its expectation over this normally distributed input, and it turns to be 1/2. Nice. Also, interestingly, So if I put here the derivative of the ReLU function, it is this function, right? And the expected value of square root derivative is also 1/2. So actually it's going to be the same coefficient if we consider this forward and backward. So in the sense, this reasoning with the forward and backward will also apply to the ReLU function. Here it was applying because we had just kind of identity nonlinearity, so there was no nonlinearity effectively. And if we had a nonlinearity, it would be different rules, but actually these coefficients turns out to be the same if we start with ReLU. So we can actually use either this formula or that formula. So okay, so what we want is that in the end the variance here on the output would have so we computed that this variance is given by n omega eta, where eta is that expectation, but we want this to be 1, right? And hence we're gonna have the initialization rule for this omega that it is 1 over n eta, or this 2 over, so like having the average number of units, right, from the two layers. And yeah, so these are the examples. For ReLU, it's 1/2. For sigmoid or hyperbolic tangent, we can just numerically compute what it is and use that as that will be like better starting point than when assuming that it was identity, right? So it's a good correction already. And then for this example, what we did here was failing with the ReLU function. So if we do this scale initialization according to these formulas, then you see it becomes then stable. So there is, now this shows statistics of activations, I believe, like after the ReLU layer. So you have this. Okay, so this is our ReLU function, right? So this, if the input statistic is centered, then half of this input is zeroed, and on the output you would expect maybe expected value of 1/2, and this is it here, and the variance is around. Okay, I don't know what is it, the variance. Okay, so we are showing not exactly what we are normalizing, but you see that the statistics of activations do not degenerate. It's stable variance and the stable expectation. Good.
Maybe two small comments. One is like we will, in the next lab, we will play with all those initializations, so you will know them very well, and we will like watch them to degenerate when you go to the corporate and so on. So it will be fine. Second practical one is in those frameworks like PyTorch, usually you don't name them Glorot and but there's like Glorot, his first name is Javier, so it's usually called Javier installation, and his first name is gaming, so it's gaming installation. So this is a little bit like confusing when you see that.
Yeah, well, now we are talking about principles, right? How it is obtained. So yeah, I give here the references. Yes, it is in PyTorch. It is implemented and has the names, and you need to also like consider that this is variance, and then they are computing the standard deviation, and they introduce the gain factor, and not this eta that I am writing here, the expected value. So they have but you can make the relation, right, to what is in the code to what is in the mass if you follow, right? Okay, then The next thing I would like to talk about, yeah, I think it's very interesting. I'm not sure it is used very much these days, but it is very interesting in the context of this kind of analysis and what else can be done, what can be improved. Some people have asked the question, okay, can we make a nonlinearity such it's not a linear function, but that still has this expected squared, there is a typo, it should be squared somewhere, squared value of 1, such that it's kind of automatically does not rescale anything. And moreover, they were interested to design such a function such that not only it would preserve the normality of the outputs, but it would even like facilitate the normality to the standard distribution, standardly normally distribution after this nonlinearity. And they did it, and they found such a nonlinearity and proved the properties. So it is such a function with some particular parameters, and its expected value that we discussed before is exactly 1. So it kind of satisfies these stable propagation rules, and then our variance initialization needs to be like 1 over n only without so because eta is 1. But the most interesting part, it's also they proved that even if the input was not normally distributed, or maybe if it was normally distributed but with no statistics which are, so it would have maybe some bias, some offset, some non-zero mean, and the variance which is not exactly 1. They show that after applying this mapping, the distribution that you get will be closer to the standard distribution. And this is like, so the theorem that they are proving is about this mapping. So we have some input statistics, and then this nonlinearity, this CELU nonlinearity maps the statistics to some other statistics, maybe after this nonlinearity and the linear transform. And the claim is that, okay, after doing that, you are getting closer to the standard distribution. And this is the diagram of that. So suppose you have some distribution which has variance which is larger than 1, and then the mean which is smaller than 0. Then after applying such a layer, the resulting statistics will be closer to 0, 1. So it not only it preserves this standardization, but it also kind of it is stable, right? So if the input is a little bit deviating from that assumption, it is bringing it closer to the assumption. And that was called the self-normalizing neural networks, and they could initialize and train deeper models, and somehow also tested on many problems that this performs better. Yeah, maybe anybody wants to compliment about this?
Well, why isn't it used then?
I would say it comes to compute now, because it's more expensive to compute than ReLU. And when you are scaling things to these very large stuff, you really care about like compute and not having to multiply things to exponent and
Okay.
yes, it depends
Uh-huh.
the specific transformer. But yes, lately they also use GALU. But like it was forgotten back to GALU, but it's
Yeah, for sure people like simplicity, and ReLU is kind of cheaper and simpler. But then they would need batch norm with ReLU to really
Like practically,
in practice.
is that often people just do something out of habit. Yeah, people did something before them, it works, so you don't change it. You just research, people use GELU, people continue to use GELU no matter what, unless somebody comes, and usually like difference is not so significant to change it, so that's why they stay with it. And like with GELU, you can obtain, when you are careful enough and do batch norm or whatever, then you achieve the same results as with this, so it's just like options, yeah?
Yeah, I think it was the case that in practice somebody showed, oh, okay, actually with ReLU we can achieve very similar results, but maybe some other tweaking or some batch normalization things, and then it sort of was not necessary to have this. Now, like a piece of background, I want to connect to this. So I want to connect this choice of the scales of the weights to preconditioning of the gradient descent, and for that we need to understand what is gradient descent and what happens with the gradient descent if we change the coordinate system. So let's consider such a setup. So suppose you have some function, and it's a function of weights. And denote its derivative as j. Then the gradient descent, yes, you know, with a constant linear rate will be this. And I forgot to fix all of the variables, so this should be w, right? So it's wt minus the gradient step. What we're gonna do is we want to change variables. So instead of w, assume we're gonna use the variables w tilde. And we can do this. So we could equivalently for the initial value. So if you started from w0 and we want w tilde to be okay. So you want this relation so that like w is a w tilde. So we can initialize w tilde 0 as a minus 1 w 0. So we can kind of equivalently reparameterize the same function in the new coordinate frame. So this was our initial coordinate frame, and this is the new coordinate frame. So this maybe is the coordinates in the w tilde coordinates after the linear transform. Now the question, if after changing this coordinate system, what will happen if we start doing coordinate descent in this space of w tilde? And we can write it out. So this is you see this is gradient descent in the space of w tilde, and the gradient of the function as a function of this w tilde is happening to be this. Because why? So because it's a composite function now. It is f of linear transform times w tilde. So we differentiate it with respect to w tilde. We obtain the gradient of f at the point aw tilde. So that's aw tilde is like our old point, the same point, but times the matrix A. So the gradient gets transformed by this matrix here once. And then, like if you look at this sequence, what the gradient descent is doing in this space of omega tilde, and kind of remap it back to the original space and see what it means for in our original parameterization. So we substitute back this relation. So we're going to express again this gradient descent rule in the tilde space. We're going to express it again in the terms of this original w. And when we do that, so this one gets substituted with a minus 1 w, and so is this one. And from this equation now we could kind of multiply everything by a on the left, and we see that the effective sequence which is obtained in the original space, it looks like this. So that this is now kind of a gradient descent step, but each gradient gets transformed by the matrix AAT. It is a positive semi-definite matrix which somehow changes. So if this was the gradient descent step in the original space originally, then by kind of mapping this point to this space, computing the gradient in that space, and doing the gradient descent in that space, we are actually moving in some other direction, right? And with a different length. And this change of the direction, so it is such that it will have a positive scalar product with the initial gradient. So it's not going to decrease the function, of course. So it still be the descent direction for the function, but only not the steepest descent in the original space. It will be the steepest descent in this skewed transformed space, right? Now, yeah, I have this illustration. So this is the contour plot of the function, and the gradient is orthogonal to the contour plot of the function, right? So the gradient descent would go in this direction for this function. But if we rescale x1 such that the contour plot becomes circular, then the gradient, it's orthogonal now in this space to the contour plot, then it will point towards the minimum. So this is kind of important. So if you have uniform scale, so if you manage to find the scaling of the coordinates or the linear transform of the coordinates such that the function contour plot is more like circular, then the gradient descent will converge faster, right? Obviously. So here it will be like maybe going this direction and then maybe going down, so zigzagging like this. Here it will go to the direction of the optimum much faster. Yeah, so that's why it is happening. It's because steepest descent is defined with respect to the particular choice of the coordinates or particular scale of the coordinates. So if this coordinate is measured in meters and that coordinate is measured in I don't know what else, grams, because we might have such a data to train the respective weights for, then you need somehow to put these two units in the same coordinate system and do the steepest descent in there, but you don't know what should be the trade-off unless you know something about the shape of this function. So you would ideally like to know maybe about curvature of this function and so to reason about the second order methods. But for now we see, so it is happening with gradient descent. It is by kind of the nature of it. The takeaway from us is that actually when we initialize these weights through the different layers differently, right? So we have this normal distribution omega 1, normal distribution omega 2. Doing that changes the rescaling of the weights, and it affects the preconditioning. We were doing that for the purpose to have stable distributions of pre-activations and also possibly kind of stable distributions of the gradient on the backward propagation. But it could be also understand that it has the effect on preconditioning the gradient descent, such that, okay, so the magnitude of the gradient in this layer is sort of commensurable, so it's kind of similar in scale to the gradient in that layer. And so it would be corresponding kind of to transforming this plot into the plot on the right if you think of sort of how the gradient is, if you think of this axis as of different layers here. Yeah, that was the idea I would like you to connect with. So this is the initialization scheme is interconnected with gradient descent dynamics.
I don't know if there's time for that, but I didn't quite get how like the normalization of the weights also like kind of transforms us to a space that is better for gradient descent. Like,
Okay, it's maybe not obvious to see that it is better, but one thing is for sure that if you change the scales, it does that coordinate transform, and it's gonna have an effect on the gradient descent dynamics. Whether it will be good or bad one, then it's a question. But yeah, it is maybe a good one in this case because we can experimentally check. Right. Yeah, we can now talk about batch normalization. So how that is designed and related to this both previous points. I think like many things can be said about this batch normalization and about its motivation. I would like to motivate it from the perspective that okay, we want to do something like this. So what we did with mass, with kind of analytically estimating the variances and statistics and centering, we can do it also without mass by just drawing samples. So we just take many images from the data. Maybe we don't need so many. Propagate it through the network and make an empirical distribution here. So rather than kind of make an assumption that this is, independent, normally distributed, and then propagated through all the layers by analytic variance and mean equations, just to do it numerically, just to take the real instances, send them through the layers of the network and see what are the statistics of pre-activations here. Right, and we could, if we have some number of them, we could plot a empirical distribution, and we could estimate the mean and variance from that small empirical distribution, and then say, okay, we're gonna like scale and shift it such that it will be standardized. So this is what the batch normalization is doing. I write it in formulas in this way that let X be kind of a matrix that consists of many data point vectors. So a batch maybe of data point vectors. And then the mean of right. Yeah. Okay. Like to define the batch normalization, you really don't need to consider the linear layer, right? So what I'm expanding here, the means and variances. But so you could just say yes. So we have the pre-activations. We could compute the mean and variance of these pre-activations and then standardize. So this is the standardization rule. So to subtract the mean and divide by this sample standard deviation. But I'm expanding here what is going to be the mean of this pre-activation if it was the result of a linear transform for the purpose of some reasoning and analysis which will come on the next slide. So for now, okay, so it's just you say you can look at this first equation that's just expected pre-activation value, whereas the expectation is this empirical one, right? So with respect to the randomly taken sample from the batch, if you like. And the weight matrix it's not random now. It's just some fixed weights. So we have initialized them, maybe randomly, but we forgot about that, and we just consider them as a known given weight matrix. And so we could compute the statistics of pre-activations and standardize them, and then we assure that for some data, or for the most of the data, our activation function, its derivative is going to be non-zero, and for some data, maybe we have a non-zero gradient, and the propagation will work. Now, this is one counterpart of it. So we kind of did initialization in the data-driven way. So, and we could stop there. So we could just once compute these distributions, apply this standardization, and then kind of freeze this mean and variance that we estimated from the batch and put them as a constants in our neural network. And that will ensure that in initialization there will be this preserved activation statistics, and it will be good conditioned from the initialization. We could do that, and that will be a kind of data-driven initialization. So people have done that, and it works well as well. But they went further. So with this batch normalization, they said, oh, okay, we're gonna keep it dynamic. So we're gonna, at every point during the training, we're gonna compute these statistics from this very same batch on which we are going to make the gradient descent step to optimize the objective. And we're going to keep give this standardization dynamic and even differentiate through this mean and variation, since it has been computed from the current batch. And it depends on the parameters in the preceding layers and so on. So we're going to keep it fully dynamic and differentiable, and then sort of train with this together. Now, to make it a reparameterization of the network, so because here we are kind of subtracting the mean and standardizing, so this takes away 2 degrees of freedom. So it has now, the network has no freedom to move this distribution to the left or to the right if it needs to do so during the learning. And to reintroduce this shift degree of freedom, there is this scale, there is this shift added on the output. And to reintroduce the scale degree of freedom, this gamma added on the output. And they are initialized as 0, 1, right? So that initially this kind of standardized, but then during the training, by changing these parameters, gamma and beta, the model can learn to shift these distributions. So at initialization, we achieve this standardization as before we did with analytic formulas. But now we're going to keep this standardization, this data dependent and dynamic, and allow it also to learn the shift and the scale as explicit parameters as this gamma and beta. So something about the properties of all of this. Yeah, so from one point of view, we are kind of doing a nonlinear reparameterization. So instead of the weight vector in our model, we are introducing the weight vector, which is normalized by the standard deviation. So kind of the scale of the weights is automatically adjusted to the scale of the inputs, and then multiply it with some gain factor, which is initially 1, but it can then be learned. And the bias is the initial bias of our linear layer is replaced by such a reparameterization, which is also kind of depends on the weight vector, on its scale, on the initial bias, and on the batch. So this constitutes some kind of nonlinear reparameterization of the neural network, and it turns out to be beneficial. So as we discussed, even linear parameterizations affect very much gradient descent. If you had such a complex function and were able to transform it to such a function via nonlinear parameterization, the better. Of course, we don't know that this is the case here, but it could be one reason in favor of using this. So if you, after this normalization, you obtain the parameterization which is somehow more favorable for optimization, then you could expect that it will train better and train faster. Yeah, at least we can see it as a nonlinear parameterization for sure. Whether it's good or not, it might be debated. The other thing that we notice is that scale is, so it is actually the question is the following. So we have this data-driven normalization, right? So this empirical distribution after the standardization is going to be standardized, so centered and unit variance. The question is then, do we still need to initialize the weights in our neural network? Well, maybe you think it doesn't matter because, okay, so this is doing that already, and it is doing that dynamically. So whatever was the weight scale of the neural networks, then it doesn't matter. So it will be kind of canceled here in the standardization. And this is true. So we could check that if we start with some weights W tilde, which is the scale times the original W, then the result of the batch normalization, so the scale will pop up in the numerator and denominator, and it will cancel. So it is the same. So if we had a linear layer with scaled by 100 and you plug it to batch norm, the output is the same. So it is invariant to the scaling. But interestingly and importantly, it does not cancel this reasoning about reparameterizations. So actually, the scale still affects the gradient descent behavior. And in the case when it is the simple scale, so we had here this AAT matrix popping out. So if it is the simple scale, what we obtain is that, like, if the scaling rule is like this, then in the gradient descent, one over the squared scale is popping out. So actually, it turns out that the scale of the weights at initialization, it plays no role for keeping this activation statistic standardized, right? But it still plays a role for this gradient descent, and now it's the only role of it, right? So it's just purely kind of controlling the local learning rate for the gradient descent step with each of the layers. And yeah, so you cannot initialize them arbitrarily. You would want to initialize them maybe the same or inverse proportionally to the number of units. So there should be some rationale to that. So you cannot just do that arbitrarily. Maybe some summary now about all this. Okay. Yeah, we discussed that this batch normalization, we could maybe use that kind of technique to do a data-driven utilization and not have it dynamic. That's one possibility. The other possibility is that we keep it dynamic and use it during the training, but then we face kind of few difficulties associated with that. Okay, if the processing of one input depends on the whole batch, so the inputs are then not treated independently, and what we are doing, we are changing the loss function. If our loss function was the expected network prediction for all the inputs independently, now it is the expected network prediction for inputs coupled in the batch through this normalization. There is maybe, you could call it a side effect or a bonus. It turns out that this actually helps for training, so it somehow regularizes the training in the stochastic way because, okay, so other instances which happen to be in the same batch are kind of taken at random. So it's this nonlinear reparameterization is stochastic. And it turns out to be, for several reasons, good for training and for generalization, and maybe this has made this technique very popular and applied in many places. Yeah, so if we keep it dynamic and batch dependent, we have these interesting bonuses. And in summary, so the weight initialization scheme still matters. So it matters if we have batch norm before the activation function as we reason it and design. So by design, we want the statistics of pre-activation to be standardized, and that was the reasoning. We could also kind of standardize the output of the activations. That works as well in practice, but then you gotta be careful with the weight initialization as well. So you cannot do the arbitrary weight initialization. Then it would work also, but the weight initialization would be doing then these two jobs: preconditioning and control of the statistics before the next activation. All right. Okay, so maybe some question or discussion to this.
What is the generally preferred way to put batch norm before the activation?
My generally preferred way is to put it before, because as I explained, so this was the reasoning, how we see what it should do, and it's somehow.
Recently there was a shift, like in the general papers, that people started to put it like I think in transformers they started putting it at at the input, so after the activation function.
I see.
Yes, but also it's not batch norm there, it's layer norm.
Oh, right, they use a different norm.
Yes, because the batch norm depends on the batch size, which can, like if you have small batch, then that's not good because the statistics could be noisy if you're using them. Also, during the batch norm time, there's a comment here that at test time you should use global statistics of mean and of like the whole data that you use during training. However, that was also very questionable whether to do it like that or measure them again on the test set. People had different opinions what you should do or not, and it was not a very standard way. So people try to move away from something that depends on the batch itself. So now it's the layer norm, but yes, now they apply it mostly after the activation. But I think how it came out was actually a mistake in like original transformer paper, when they accidentally did it and it was performing better, so people use it. But I can try looking if there is some specific, like more theoretical study of before or after, and why would it work better in the way. But I think like actually how we come up with this was like someone accidentally put it there, and most transformer libraries now actually have you the option to say before or after.
It's an evolution, right? And often it is random, but then what works better survives.
We're doing stochastic gradient descent.
Yes.
In learning,
This
machine
whole-
learning.
this whole field, it's quite.
Yeah.
Same thing what Jan mentioned about the activations. Someone starts using them, it kind of works well, and then everyone follows, although it might take some time for people to catch up and actually maybe find theoretical explanations why.
Could be just that the parameters are also fine-tuned for this particular setup, so that people are using it.
Of course.
So we just need to find different parameters, and then maybe you can beat this setup. Yeah? But it's usually so expensive that doing these experiments.
Yeah, of course. There are so many changes changes you can do to the architecture, that this is, yeah, usually ends up fine.
Yeah, we will have a lecture on transformers. Maybe we could discuss there about these details as well.
Yeah. For the transformer lecture, yes, and yeah, definitely maybe also talking about wire norm and something like that we could introduce, at least in the transformer lectures. I mean, we will have to, it's used there. It's a small change, but
Do they use some weight standardization together with this? Is it enough to have this layer norm?
I think they use something, but now I cannot say specifically what it is. It's
Right.
probably something quite basic because it's pretty much like the linear layers stuff with activation. It would be some of the standard one, I think. Nothing too specific, but they use it. It would be either Hay or Glorio, but I'm not sure which one.
Okay, so last piece for today, residual neural networks. Maybe somebody already is familiar with them. And you mentioned in the beginning that it could be one way to improve our training performance. And indeed, like what the pilot experiment that they are showing in the ResNet paper is that now with batch norm and stuff, we can train pretty deep networks. But somehow, if you want to train a very deeper network, the training is not performing well. And so this is a comparison, maybe, so this is the training error versus the number of iterations. So the 20-layer network. So here they are using this, wow, maybe cascading learning rate. So there is the decrease of the learning rate at this step, and it drops sharply. We will discuss about this in the stochastic gradient descent lecture. But the point here is that, okay, so the 56-layer network is kind of training much slower, and in the we always have a limited training budget, and we are trying to train on as much data as possible. So it is an issue. So we cannot wait 10 times longer for this to finish. And moreover, it turns out that the things that you have to train longer, they do not generalize that well. So somehow what you want is really fast and efficient training, such that from the same number of considering the data batches, it would generalize better to fit better the other training data as well as the test data. So, and this is what you would want to observe already on the training plot as a fast training trend. And this was not happening. So you take a deeper network, you solve the issue with these vanishing gradients via this initialization and batch norm, or just batch norm. But it's not possible to train a deeper model, or it is possible, but there is no gain, right? So we are doubling the number of the layers or tripling the number of the layers, but it's not leading to better training or the test performance. And then what they proposed, okay, so we need maybe not just a plain deep architecture, but we need to create some shortcut connections in this architecture such that it would be a combination of, so in this network architecture, there would be passes that go through many layers and passes that go through fewer layers. Yeah, so if you look at this figure, so this is the basic design of the skip connection. So we have maybe a group of layers, 2 or 3, it depends, maybe 1 if you like. What is important here is that, okay, except of going directly through this sequence of layers with linear and nonlinear transforms, you have a skip connection that bypasses that, and it is added to the output here. So in this way, the architecture that you create is not like a sequential graph of layers, but it is a graph with different passes, and the depth of this architecture is not precisely defined, right? But there is a maximum depth of all the nonlinear layers if you look at that pass, or there are other passes which are kind of skipping some of the nonlinear layers, and then these passes are shorter, and that together that works nicely. Now we can look a little bit at the different views of doing this. So one view is to discuss what is residual connection, why it is residual. And to explain this, I would like to bring up this example that discusses about residual learning. So the idea is that let's consider a regression problem. And the idea is that, okay, so suppose we have some regressor F0 of the target X star, and suppose we train that already. And now after we train that, after we fit the target with one neural network, there is still kind of a residual difference between our prediction and the targets. And this is the residual error, right? And now what we can do, we can take these residual errors and try to train another model to regress this residual errors, like to correct the error of your previous prediction. And we could, like mathematically, we could write it as, okay, so this is going to be our target, so the residual of the previous prediction, and this is going to be a new predictor that its goal is to compensate for this error, right? And if you do that, we discover that the corrected predictor, so if you open these brackets, the corrected predictor for this original target will be x1 plus the f1, so it will have this form. So you kind of take the predictor by the first network and then add to it the prediction by the second network, which could be, in this case, a function of this first prediction as well. And so this I explained as like doing it in the step-by-step. It's possible to do it also in practice like that. It has been done in some cases like that. So if you have some neural network trained for one scene, you could add on top of it some post-processing layers, which with the goal of these layers to compensate some residual errors. It has this kind of training has been done for, let's say, maybe a nice illustrating example is this sort of optical flow, whereas there it is indeed a regression problem. So you want to say where each pixel has moved when you go from the one frame of the video to the next frame of the video, right? And you do some prediction, and there is a ground truth. So, but then you discover, okay, these are mostly okay, but maybe somewhere like there is this small residual errors, and somewhere a couple of large errors, and then you could train a few more layers to post-process this to sort of reduce these errors. I don't think it gives us like as much of the mass or the insight about the residual networks, but it kind of, at least it explains the term of the residual concept in here, and maybe relates to some history. Maybe except of mentioning the he et al. For this deep residual networks, I should be mentioning Schmidt-Gruber, who was doing it for LSTM models for the recurrent neural networks. But it turns out that also, so it turns out that people been looking at this kind of architectures even in the Rosenblatt's perceptron and even before, and biologically inspiring, they were considering this already much earlier, and then in some other models. So in the context of the recurrent neural networks of this Schmidt-Gruber, this was motivated by the vanishing gradient problems, and it helped there. Here, he told, so they started already from batch normalization models, so they kind of did not see an issue with vanishing gradients, but they still had the issue with that, okay, it does not train as well as you would like to, so what we can do? And yes, so it's sort of architectural solution that turned out to be training better. We could maybe reason a little bit why it is training better. So maybe that's a kind of alternative view of this model, is sort of to imagine that there is a long skip path, sort of mostly identity mapping, with much fewer layers on the skip path, maybe that they're doing the adaptation of the number of channels. And like residual branches are sort of added here like this. So they kind of computing something based on the current input and correcting the current state. And if you have many of such layers, then the model is that, okay, each such residual pass could be making just a little correction of the output, and then you could have many of them, and then each residual thing is making a small correction. And what we can see from this kind of diagram is that if you look at the backpropagation, so there would be maybe pretty much straight path to like almost identity path to any of these residual blocks. Right, so if you consider like the path going through this identity, the highway path to the residual block, so the gradient will propagate here. So the plus copies the gradient, right, on the backpropagation. So the one copy of the gradient goes here, and the one copy goes here, and then it's happening in every plus, right? So then every block receives its copy of the gradient from the loss, if you like. And yeah, maybe this view explains why it is somehow well conditioned and also addresses this gradient propagation, so addresses the vanishing gradient problems if you had many sigmoids maybe in this network that would resolve that. Yeah, okay, so we are at the end of the lecture. Just to mention, there are kind of, in practice, there are many variants of this with respect to how to place and where to place the other layers, such as nonlinearities, batch normalization, and so on. It somehow has stabilized maybe to this variant of the architecture where you are trying to preserve as much of the identity straight through paths as possible. There were some other like variants regarding what to do with this plus. Maybe it should be a convex combination, a parameterized convex combination or not, how to initialize this linear combination. So maybe there is some there are variants with some gating, so some kind of coefficients estimated based on the data, how you mix the skip path and then the residual path. So there are other variants regarding the architecture design, so what you combine and how you combine. Like the takeaway, I think, for us is that, yes, so having such a skip connections and sort of multiple passes to the loss that combines shallower architectures and the deeper architectures into one, that's beneficial for training, so that then the training can go faster. And the predictor can be viewed as sort of, in some understanding, it is ensemble of all these different networks. So it is ensemble of the network that is maybe doing this and go into the to the prediction plus the network that is doing this and that and go into the prediction, right? Because of these pluses, it is kind of a sum of many predictors, if you like. And it is an ensemble, kind of couplet ensemble. Yeah. Okay, just maybe last point. There is depth versus width trade-off. So as I mentioned, maybe somewhere in the beginning, you could improve the training also by just plainly increasing the width of the network. And so this experiment shows, like, for networks of different depths, if you increase the width, so this width factor, then the performance improves with any depth. Yeah, so that's one point, that okay, so you can have consistent gains from just increasing the width of the networks. Maybe you could notice here the pattern is that the best performance is for the network that has the maximum number of parameters. So here, or the 52 millions for this larger set. So that's like one trend. And yes, if you think of it, then doubling so people have trained these residual network architectures with depths of 100 or even 1000, but the returns are diminishing, right? So how much better it solves the problem is maybe increasing the accuracy by a little bit, whereas maybe you are increasing the depths by a factor of 2 each time or so on. So we are back to also to the questions of efficiency, right? So we cannot really, even if it is experimentally looking good to increase the widths and depths, we cannot do this infinitely because we are also bounded by the resources. So we can get back again to the discussion, okay, how actually much memory activations and compute we are spending, and what is the good architectures that are performing well with respect to that as well. But on the other hand, if we were able to train some wide and deep neural network and it performs well, it turns out that we could sparsify it, so we could like discard lots of weights from this network, and it would be still performing weight, maybe like 95% of the weights, it would still be performing well. And so it turns out that a lot of this initial width and capacity was redundant. It was there just for that at initialization, due to the randomness, there was something by chance which is favorable to learning, and then the learning picks up on that, and then the rest is kind of not needed. So this is like one view how the things are working. So it is possible to sparsify the result a lot after the training, or distill it with a smaller model. So it's possible to do that sort of things as well. Oh, yeah, I'm terribly sorry. I'm already too much overdue. Okay, thanks.